We present our paper Adaptive Multitask Learning for Few-Shot Object Detection. Generic object detection requires great effort to prepare densely annotated data for learning. In some data-scarce scenarios, it is very difficult to collect adequate data. Few-shot object detection aims to detect novel objects by generalizing knowledge learned from base-seen classes to novel unseen classes, with sufficient training samples in the former and limited training samples in the latter. In this figure, we find that generic detection with abundant training data leads to balanced classification and regression IOU scores, while the few-shot setting shows higher score misalignments. The gap between classification and regression widens notably in few-shot scenarios compared to generic object detection. Object detection is a multitask learning problem involving two subtasks: classification for determining what class the object belongs to, and localization for determining where the object is. They have two distinct differences: conflicting translation and scale properties, and conflicting backward task gradients. The discrepancy becomes more pronounced in few-shot settings as opposed to the generic detection problem. Any bias toward either task would negatively affect the performance of FSDO. Multitask learning could be a good solution for these problems, which leverages a joint model to concurrently address multiple predictive tasks. However, the negative transfer problem arises when tasks have conflicting requirements. The conflict in learning dynamics can be detrimental, rather than beneficial, to the learning process. To mitigate this issue, three strategies can be considered: decoupled models, gradient modulation, and enhanced task-specific branches. To decouple classification from regression, we enhance the baseline with a double-head RCNN, dividing it into task-specific branches for classification and localization using Res5 residual blocks. This straightforward enhancement leads to improved performance over the baseline. Building upon the enhanced baseline, the proposed method addresses the conflicting requirements of the two tasks by rescaling the backward gradients of the two task-specific branches before forwarding them back to the backbone. A novel precision-driven gradient balancer is introduced to dynamically harmonize the learning process with a double-head RCNN model. This balancer, pre-trained on a few-shot data set, exhibits the capability of adaptively rescaling the backward gradients from the classification and localization heads. This adaptive rescaling not only proficiently alleviates the gradient conflicts, but also substantially elevates the learning performance. Moreover, to enhance individual tasks, we devise a knowledge distillation and score refinement scheme named KDSR, leveraging both image and text embeddings from a pre-trained clip. During the training phase, clip is adapted as a teacher network to guide the learning of the classification head. During the inference phase, clip is further adapted to aggregate the detection scores. This scheme effectively inherits clip's powerful capabilities, particularly critical in data-scarce scenarios. In contrast to the previous method, which solely leverages clip's text encoder, KDSR aims to unleash the full potential of clip for FSOD by utilizing adapted image text features. This table shows a comparison between the SOTA-MTL gradient modulation methods and the proposed precision-driven gradient balancer. Through adaptively rescaling the backward gradients, the proposed balancer with the double-head RCNN boosts the average precision of FSOD by 11.3% compared with the baseline. Compared with other methods, our gradient balancer can adaptively generate different ratios for different few-shot conditions. Meanwhile, our results are surprisingly similar with the choice of grid searching. In contrast to grid searching, which employs time-consuming brute force searching, the gradient balancer provides a more time-efficient and parameter-efficient solution. The experimental results demonstrate that the proposed method achieves state-of-the-art performance on benchmark datasets. We further illustrate the detection results of both the proposed method and the baseline in this figure. Our method demonstrates superior IOU scores in terms of localization and higher detection scores in terms of classification. That's all for this video. Thanks for watching.